Write the following rational numbers in their decimal form and also state which are terminating and which have a non-terminating repeating decimal. So first we have an improper fraction for the first bit, that is 3 by 8. So let me solve it using the long form of division to convert into a decimal form. So 3 divided by 8. So since 3 is less than 8, I will keep a decimal which so that we can write a 0 next to 3, and 8 3s are 24. So we'll have a remainder 6, and since we have already a decimal we can include a 0 here. 8 7s are 56. So we'll have a remainder of 4 and again a 0 next to 4, and 8 5s are 40. So the final remainder is 0. So we can write 3 by 8 equal to 0.375. So since after the decimal there are only 3 digits, we can say that this is a terminating decimal. Again, for the second bit we have here 229 divided by 400. So 229 divided by 400, we'll include a decimal here, 0. So 400 into 5, that would give us 2000. It will give us a remainder of 2090. Since we have a decimal, we can include a 0. And 400 into 7 would give us 2800. Again, we'll have a remainder of 100, and we can include a 0 after this since we have decimal. So 400 into 2 would give us 800 minus 200, and again a 0. 400 into 5 give us 2000 minus 0. So the final remainder is 0. Now we can write the improper fraction, 229 divided by 400 equal to 0.5725. Since after the decimal we just have 4 digits following, we can write this as a terminating decimal. For the third bit we have here a mixed fraction. First let us convert that into an improper fraction. So that would be 5 4s are 20, 20 plus 1, 21 divided by 5. 21 divided by 5. 5 4s are 20. So we'll have remainder of 1, and we'll keep a decimal, and we'll have a 0 here. So 5 2s are 10. So 4 1 by 5 mixed fraction can be written as a 4.2 in decimal form, and since after the decimal we have a single digit, we can write this as a terminating decimal. For the fourth bit we have here 2 by 11. So long form of division again, 2 by 11. So since 2 is less than 11, I will start with the decimal, 20. So 11 ones are, I have remainder of 9, again 0. 11 8s are 88. We'll have remainder of 2. Again, since I have a decimal here, I can write a 0. Again 1s are, so I'll have a remainder 9 here again, 90. 11 8s are 88. So you can see that the numbers are repeating. There's a pattern here forming. So and this division will continue to take place. So this is non-terminating decimal here. And we can also see that after the decimal, the numbers in the quotient are also repetitive. We call this sort of decimal as a recurring decimal. So 2 by 11 can be simply written as 0.1818, so on. Or a recurring decimal can also be written like this, 0.18 with a bar on top showing that 18 would be repeating after this. So this is a non-terminating repeating decimal. For the last bit we have here 8 divided by 125. Using long form of division, 8 divided by 125. I'll apply a decimal since 8 is less than 125, and again 80 is also less than 125, so I'll include another 0. So I have here 800. So 125 into 6 would give us 750 and would leave us with the remainder 50. And since we already have a decimal, we can include another 0 here. And 125 into 4 is equal to 500. So final remainder is 0. So 8 divided by 125 is equal to 0.064. Now here we have a terminating decimal. Now if we categorize the above problem into terminating and non-terminating decimals, we have here 3 by 8, 229 by 400, and 4 1 by 5, and 8 by 125 as terminating decimals. They produce terminating decimals, whereas the fourth bit 2 by 11, which gives us 0.1818, and so on, repeating non-terminating decimal. So what do we observe from these answers? So here you can observe that the decimal is the determining factor to say if it produces a terminating decimal or not. Here we can observe that the decimal 8 has prime factors 2, so it can simply written as 2 cube, and similarly 229 by 400 can be simply written as 229. In the terms of prime factors, it can be written as 2 square into 2 square into 5 square, or 2 power 4 into 5 square. And 21 by 5, the prime factor is 5 here, and 8 by 125, in terms of prime factors, the denominator can be written as 5 cube. So since these are terminating decimals, we can observe that the denominator should either have prime factors 2 or 5 or both. And here you can see in the non-terminating decimal that the denominator has the number 11, which has neither the prime factors 2 or 5. So from this we can write the theorem that a rational number in the form of p by q, which has a decimal expansion that terminates, can be expressed as a rational number whose denominator is a power of 2 or 5 or both. Or simply put, if a rational number is terminating decimal, denominator should be of the form 2 power n into 5 power m, where n and m are any natural numbers.